Welcome back to Maths in an Empty Classroom with me, Mr. Southern. This is part 2 of the video on differentiating exponentials and logarithms, and in this video I'm going to be looking at how to differentiate luns and going through some examples. So first of all then, if we have the function, the natural logarithm y equals ln x, that differentiates to 1 over x. So what that then means is, if we have y equals k ln x, where k is a number, ln x differentiates to 1 over x, but because we have k lots of that, we would get k over x. And the reason I'm identifying this as an example is students often get confused with what happens with k ln x and what happens with ln of kx. Now, what happens with ln of kx? Well, let's just have a think about how else that could be written. If you think about your ln rules, it's possible to write ln of kx as ln of k plus ln of x, because if you have a product inside a bracket with a log, you can write it as two separate logs added. It's the addition rule of logarithms. And what's ln of k? Well, ln of k is a number, so that's going to differentiate to 0, which means actually we're differentiating ln x, and therefore we get 1 over x. So you can think about differentiating luns in terms of transformations. However, a more effective general strategy is to say that if y is ln of a function of x, a bit like the e to the function of x in the previous video, then for dy dx you get 1 over the function, so whatever's inside the bracket, and then it is multiplied by the derivative of the function, the differential of the function. So it's 1 over bracket times by differentiated bracket. And if I apply that thought process to this up here, if I were to write 1 over the bracket, so 1 over kx, and then multiply it by the differentiated bracket, kx, k is a number, so kx would differentiate to k, and you can probably see what's going to happen there is that k is going to cancel that k to be 1 over x. So I've got the same result there. And because that number k is always going to be the same as that number k, that cancelling will always happen. So think about it as, if you're differentiating a ln, it's 1 over the bracket times by differentiated bracket. And we're just going to do 4 examples of that to get you to get the hang of it. But before I go through them, pause the video and have a go yourself at each of the 4. 1 over bracket times differentiated bracket. Okay. So number 1, if y equals ln of x squared plus 7, so this bit is the bracket, so dy dx would equal 1 over x squared plus 7, the bracket, and multiplied by the differentiated bracket, which in this case would be 2x. And I would write that result as 2x over x squared plus 7 for my dy dx. It's okay. Similarly here, y equals ln of 3x squared. I would write that dy dx equals 1 over 3x squared multiplied by the differentiated bracket, which would be 6x, which would be 6x over 3x squared. Actually, you can do a bit of cancelling here, because you can cancel that x with one of those x's. The 6 cancels with the 3 to be 2 over 1. So it actually comes out to be 2 over x. And you could just have a think about how you'd split this up using your ln rules. You could write this original expression as ln 3 plus 2 ln x, because you'd have ln 3 plus ln of x squared, bring the 2 down. Ln 3 is a number, differentiates to nothing, and 2 ln x differentiates to 2 over x. So sometimes it's possible to think in terms of transformations as well, but the key message there is to make sure you simplify your answer to 2 over x for dy dx. Right, similarly here, y equals ln of sine x, so dy dx, 1 over the bracket, so 1 over sine x, and then multiply by the differentiated bracket. Well, we've learned that sine differentiates to cos, so it'd be multiplied by cos x. So you could write that as cos x over sine x, or if you were feeling flash, cot x. And if you look in the A-level formula book, you look up the integral of cot x, it will tell you that it's ln of sine x, and there's y. Finally, we've got this rather nasty looking one here, y equals x cubed plus ln 5x, all in a bracket squared. Because we've got something in a bracket to a power, we're going to crack out the chain rule. So power down, so 2, lots of x cubed plus ln of 5x, because the bracket stays the same. Reduce the power by 1, and then multiply by the differentiated bracket. Now, differentiated bracket, x cubed is going to go to 3x squared, and ln of 5x is going to differentiate to 1 over x, because it's one of them. Ln kx, ln of a number of x, will always differentiate to 1 over x, and you are allowed to just jump straight to that, as I have, without showing the method of it being, in this case, 1 over 5x times 5. Notice I've put the bracket round those two terms because it's a two-term function, the derivative, and all I'm going to do just to finish this off, I'm not going to mess around trying to expand it out because it's yucky. I'm just going to write 2, lots of 3x squared plus 1 over x, and then x cubed plus ln 5x. And that is my expression for dy dx for that function there. And that is job done. Thank you very much for your company.